Hello guys, and welcome to this video on continuity and differentiability. So let's take a look at the question. We're required to identify and give the type of discontinuity in each of the following functions. So the first function is x minus 2 divided by x squared minus 4. The second question is 1 divided by sine x. The third function is x raised to the power of 4 divided by x raised to the power of 3. And the fourth function here is a piecewise defined function which has a value of x plus a when x is greater than 0 and has a value of a minus x when x is less than 0. The fifth function we are going to be considering is the derivative of f of x for f of x in question D. Then the last question here is f of x raised to the power of 2, where f of x is equal to the derivative of absolute value of x. So to solve this, we have to establish the main types of discontinuities that we have. So for functions generally, there are three types of discontinuities. So we have the removable discontinuity, second type of discontinuity that we have is the jump discontinuity, and the third type of discontinuity that we have is the asymptotic discontinuity, or sometimes it's called an infinite discontinuity. So I would briefly explain what each of these discontinuities mean, then we can take a look at it in the functions that we've been given. So a removable discontinuity is a single missing point in a curve, and it can be removed by modifying the function at that point. And most or all every removable discontinuity you find is represented with a hole or a unified circle of some sort. So if you see a function and you see a hole in the graph of the function, that's trying to tell us that there's a removable discontinuity in that function. And the good thing about removable discontinuities are you can always eliminate them from the function by changing or modifying the function. We would see how we can do this in these examples that we have here. The second type of discontinuity that we have is a jump discontinuity. So a jump discontinuity is a gap in the function where it approaches different values from the left and the right hand sides. In the last video on limits of functions, there were examples that we solved where we saw that the right hand limits and the left hand limits were not equating to the same values. Hence, the limit of the function not being existent because they have different values. So if you have a case like that in a function where as a function approaches a particular value in the domain from the right, it has a different value from when it approaches it from the left, then we say the function has a jump discontinuity. So say for example, we have a function that has a value of x is equal to, or as we check the limit of the function as x tends towards 2, for instance. As it approaches it from the left, if the function has a value of say 0, and if it approaches from the right, it has a value of say 1, then it means there is a jump there. It went from 0 to 1. There was a leap, a jump. That's where the name jump discontinuity is coming from. And the functions, they have to have defined values. So in as much as they approach different values, the values must also be defined. That is, it should be a number. You can't have infinity in that case. So that is a jump discontinuity. In an asymptotic or an infinite discontinuity, it is a discontinuity that occurs at a vertical asymptote. Now, what is a vertical asymptote? Before we go there, remember that we discussed in the last example on limits in the previous video, we were required to find the horizontal asymptote of a curve. That's trying to evaluate the behavior of the curve as x tends towards infinity or negative infinity, as the case may be. So either ways, if you check the value of the curve as it approaches x, as x tends towards infinity or negative infinity, then it means we can get the asymptotes, the horizontal asymptotes of the curve at that point. So now for a vertical asymptote is where the function heads towards either positive infinity or negative infinity, and it is drawn as a vertical dotted line on a curve. So if you evaluate the limits of a function and you find out that from the left or from the right it approaches either positive infinity or negative infinity for a given value of x, then we say the function has a vertical asymptote at that point, which is going to be represented as a dotted straight line, and that is a point of discontinuity known as an asymptotic or infinite discontinuity. So since we've established that for the three of them, so let's take a look at these functions now. So the first function that we have there is this: x minus 2 divided by x raised to the power of 2 minus 4. If we take a look at this function, at x is equal to 2, that is x is equal to plus or minus 2, it is evident that if we substitute minus 2 or plus 2 into this, they are going to be having, let's say at x is equal to 2, we're going to be having 2 minus 2 divided by 2 raised to the power of 2 minus 4. So this is going to give you 0 divided by 0, which is an indeterminate form. So at x is equal to minus 2, for instance, then you have this to be minus 2 divided by, sorry, not x again, minus 2 squared minus 4. And this equates to minus 4 divided by 0, making the function undefined at this point. So these are the two values of x at which this function is undefined or does not have a value. So at x is equal to 2, we can eliminate any issues with that by restructuring the function. So we can simplify the denominator as x minus 2 divided by x minus 2 x plus 2, that is using difference of two squares. But now it means we have the original function to now be equal to 1 divided by x plus 2. So it means we have eliminated the discontinuity that occurred as a result of x being 2, which means by simplifying the function to this and substituting x is equal to 2, we now have a value of 1 divided by 2 plus 2, which gives us 1 over 4. And since we've done that, we can say we have a removable discontinuity, since by modifying the function, we have been able to remove that discontinuity. But what of at x is equal to minus 2? So here, let's make that conclusion. The function has a removable discontinuity at x is equal to 2. But on substituting minus 2 even into this modified function, you're still having an undefined value. You have 1 divided by minus 2 plus 2, which is 1 divided by 0, and that's undefined. If you evaluate the limit of the function at this point, you would see that as x tends towards minus 2 from the right, the value of the function tends towards negative infinity, and as x tends towards minus 2 from the as x tends towards minus 2 from the left, the value of the function approaches negative infinity, and as x tends towards minus 2 from the right, the value of the function approaches positive infinity. So this means at x is equal to minus 2, we have an infinite or an asymptotic discontinuity. So those are the two types of discontinuities that we have in this function. Let's take a look at the second question. Second question we have there is let's f of x is equal to 1 divided by sine x. So we know that all the values of sine x range from minus 1, or they range between minus 1 and 1 generally. So you have values from minus 1 to 1 depending on the value of x that has been substituted into sine x. But we also have points where values of sine x is equal to 0. So this makes the denominator to be equal to 0, and thus making the function undefined at those points. So at every point where sine x is equal to 0, we have the function being 1 divided by 0. And since we can't modify the function to eliminate that discontinuity, then it means we don't have a jump discontinuity, a removable discontinuity, sorry, at that point. Then there is no jump discontinuity since sin x is, there are no situations where sin x doesn't approach the same value from the left and from the right. It is a smooth function, it is a continuous function. So we can't say there's a jump discontinuity there. But at that point, at those points where the values of sin x is 0, we have the fx to be undefined, and we have the values tending towards infinity or negative infinity at those points. When you look at the right-handed limits, you look at the limit from the right-hand side, you look at the limit from the left-hand side, so they tend to either positive infinity or zero negative infinity, thus buttressing or showing us, so they tend to negative infinity or positive infinity, and this is indicating that at those points we have vertical asymptotes, and hence we have asymptotic discontinuities at various points in the graph of sin x within the domain. And since the domain has not been specified in this case, it's safe to say we have various vertical asymptotes. If you want to have an idea of what the function can look like, or the function will look like, then you would need to graph the function, and you will mostly have something that looks like this. So you're going to have a lot of functions that look like this. And at this point, you're going to be having vertical asymptotes. And this goes on and on like that for various points where sine x is equal to 0. So this is what you're going to be having. You can confirm this by graphing the curve. The next function we have there is x raised to the power of 4 divided by x raised to the power of 3. So it is this function is defined at every point on the function or every point on the Cartesian coordinate except at x is equal to 0. So at x is equal to 0, we are going to be having the function as 0 raised to the power of 4 divided by 0 raised to the power of 3, and this becomes 0 divided by 0, which is an indeterminate form. So for this reason, we have to take into account what happens at x is equal to 0. But this can be solved by simply dividing the function. So on dividing the function, it becomes x raised to the power 4 divided by x raised to the power 3, which is x. And at x is equal to 0, you now have that the function has a value of x is equal to 0. So the function can be defined at that point, which means by making modifications to the function at x is equal to 0, or the function generally, we are able to solve for the value of the function at that point. So it means there is a hole there, or there is a jump discontinuity, because originally the function wasn't defined, but we could find the limits by evaluating and restructuring the function or simply modifying the function. It means for the function x raised to the power 4 divided by x raised to the power 3, there is a removable discontinuity at x is equal to 0. So the next function that we'll be looking at is fx is equal to piecewise defined function x plus a when x is greater than 0 and is equal to a minus x when x is less than 0. Sorry. So this means when we take a look at the left-handed limit, we take a look at the right-handed limits, we can see that at x is equal to 0, the function is not defined because we're only given the values for x greater than 0 and x less than 0. You can see that the function is not defined at x is equal to 0. But on substituting, or when we try to find the right-handed limits, that is the limit of f of x as x tends towards 0 from the right, that's going to give us 0 plus a, which is equal to 0. And this is the same value as the limit of f of x as x tends towards 0 from the left, which is equal to a minus 0, which is equal to a. So it means the limit of the function as x tends towards 0 exists and it is equal to a, but the function is not defined at that point in time. So we say there's a hole in the function, and hence f of x has a removable discontinuity. Let's take a look at the fifth function. The fifth function said we should find the discontinuity in prime of x, where f of x is this function that we've considered there. So on differentiating the function, we have this to be 1 and we have this to be minus 1 for x greater than 0 and x less than 0 respectively. So on looking at this, as x tends towards 0, you can see that the limit of x as x tends towards 0 from the right is going to be 1, and the limit of the function f prime x as x tends towards 0 from the left is going to be minus 1. And this means the limits approach different values as x approaches that number. So hence there's a jump in the values of the function, and as such the function has what we call a jump discontinuity. For the last function that we'll be considering here, it is said that we should find discontinuities in f of x all squared, where f of x is the derivative of absolute value of x. Now, absolute value of x is defined as minus x for x less than 0, is defined as x for x greater than 0, and is defined as 0 at x is equal to 0. So now f of x is defined as the derivative of absolute value of x. When evaluating the derivative of absolute value of x, we have it to be minus 1 for values of x less than 0. We have it to be 1 for values of x greater than 0. So at x is equal to 0, the derivative is not 0, but it does not exist because the derivative as it tends towards 0 from the left is different from the derivative as it tends towards 0 from the right. So we say the derivative does not exist at x is equal to 0. So f of x all squared now means we have minus 1 at x less than, sorry, so that means we have 1 for x less than 0, 1 for x greater than 0, and at x is equal to 0, the derivative does not exist. So it means since the limit as x tends towards 0 from the right is equal to the limit as x tends towards 0 from the left, and the value is 1, the function doesn't exist at x is equal to 0. So we have a removable discontinuity at that point. So let's take a look at the second question that we will be solving. So the second question says that we should find the values of the constants a, b, and c for which the following function is differentiable. And we are required to give a and b in terms of c. So the function is f of x is equal to cx squared plus 4x plus 1 for x greater than or equal to 1, and we have ax plus b for x less than 1. So it's first required that we should understand what the continuity and differentiability of a function means. A function is said to be continuous if its right hand limit is equal to its left hand limit, and this is also equal to the value of the function at that point. So if we are evaluating the function at a point A, it means the limit of that function as x tends towards A from the right should be equal to the limit of the function as x tends towards A from the left, and is also be equal to the value of the function at point A. Then you say the function is continuous. So a function is said to be differentiable at a point if it has a derivative at that point. And all differentiable functions are continuous but not all continuous functions are differentiable. So that's a very, very important thing to note. All differentiable functions are continuous, but not all continuous functions are differentiable. I think it's something that should be written down. And it's also important to note that any function that is continuous and smooth is a differentiable function. So using these facts that we know, we can solve this question. So they said the function is, we should find the values of constants a, b, and c for which the function is differentiable. So it means we first check the continuity condition, then we go ahead to do the differentiability condition. So for continuity, we have that limit of f of x as x tend towards 1 from the right will be equal to the limit of cx squared plus 4x plus 1 as x tend towards 1, because that's the function that defines the value for x, values of x that are greater than 1. So we have this as c into brackets 1 squared plus 4 into brackets 1 plus 1. So this becomes c squared plus 5. Then the limit of f of x as x tends towards 1 from the left will be equal to the limit of, as x tends towards 1, of ax plus b, and this becomes a into bracket 1 plus b. So this is a plus b. From the conditions of continuity, the left hand limit and the right hand limit must be equal. So we have c squared plus 5 is equal to a plus b. Sorry, not c squared. It should be c plus 5. So c plus 5 there. Then we have a plus b. So if c plus 5 is equal a plus b, we can write this as our first equation. So for differentiability, we evaluate f prime x. So f prime x will now be equal to 2cx plus 4 for values of x greater than or equal to 1. Then we have it as a for values of x less than 1. So we now evaluate f prime x at x is equal to, as x approaches 1 from the right and as x approaches 1 from the left. So f prime of x as x approaches 1 from the right is going to be equal to 2c into bracket 1 plus 4, which is equal to 2c plus 4. Then we have f prime as x approaches 1 from the left. This becomes a. So it is evident that a will be equal to 2c plus 4. This is the value of a in terms of c. So here from equation 1 we stated that c plus 5 is equal to a plus b. So we have c plus 5 to be equal to 2c plus 4 plus b. So this now becomes If you collect like terms, b becomes c minus 2c plus 5 minus 4. So b becomes 1 minus c, and this is the value of b in terms of c, for which the function is differentiable. So let's take a look at one more question. We're required to find the values of the constants a and b for which the function is continuous but not differentiable. Remember that all differentiable functions are continuous, but not all continuous functions are differentiable. So the function is given as follows: fx is equal to ax plus b for x greater than 0 and is equal to sine 2x for x less than or equal to 0. So let's take a look at the conditions for continuity by evaluating the right hand and left hand limits. So limit of f of x as x tends towards 0 from the right will be equal to the limit of ax plus b as x tends towards 0, and this is going to be equal to 0 plus b, which is b. So limit of f of x as x tends towards 0 from the left is the limit of sine 2x as x tends towards 0. This is sine 0 and this is 0. So therefore, we have that b is equal to 0. So if it is not differentiable, let's find f prime of x. So f prime of x now becomes a for x greater than 0 and 2 cos 2x for x less than or equal to 0. So to find f prime of x as x tends towards 0 from the right, we have that to be equal to a, and f prime as x tends towards 0 from the left, you have 2 cos 2 into bracket 0, and this is equal to 2. So if since it's not going to be differentiable, it means the values of the derivative as x tends towards 0 from the right should not be equal to the value of the derivative as x tends towards 0 from the left. Therefore, a is equal to minus 2. A is not equal to minus 2 for the function not to be differentiable. So to find the values of a and b for which function is continuous from and but not differentiable is b is equal to 0 and a is not equal to minus 2. So which means as long as a is not equal to minus 2 and b is equal to 0, the function is going to be continuous but not differentiable. And with this, we've come to the end of this video on continuity and differentiability. I hope you guys enjoyed it. See you guys in the next video.